Like, what kind of confidence are you so?
Is that hard?
Like, yeah, it was one that I started this with too, but I have they had it all right now.
All right. I mean, we have okay.
Are those kind of games when they get an upset?
That's why you still got to play the game. Yeah, still got to play the game. If they're a D1 school and you're a D2 school, you don't play with the confidence they do.
Okay, last little bit of info on the chapter 5. All right, so we've been looking at this redistribution of blood flow. Okay, so we've got to move blood from areas where it's doing a lot of work, providing nutrients and providing oxygen when we're at rest, to the heart and the skeletal muscle when we're exercising. Right? So we've got this mechanism in place to try to direct the blood flow to the place that we need it to be to provide enough oxygen so that we can make ATP and exercise for a long time. Okay? So remember that being able to direct the blood involves either dilating the blood vessels where we want the blood to go and or constricting the blood vessels that are taking blood to an area that isn't crucial when we're exercising. Right? So, stomach, you don't want to eat a lot because we redirect blood flow away from the stomach. Also, your kidneys. You might have noticed if you go out and you're exercising for a long time, the longer you exercise, the less you want to run in and use the toilet. Right? Partly because we absorb that water to try to help us stay hydrated, but also because we move blood flow away from the kidneys and so they're not doing their job to create urine. All right? Okay, so last piece of the pie is looking at how do we get that blood that's in the veins back to the heart, particularly against the pull of gravity. Right? So at rest, the veins are very elastic. About 65% of your blood is in your veins while you're resting. So they act like a reservoir. Right? We said that we have to direct this blood flow. We don't suddenly make more blood when we start exercising to produce the nutrients that we want. We just move it from somewhere else. Okay. So 65% is sitting there in this reservoir when you're at rest. So you may notice if you're sitting for a long time that your ankles seem to swell. Part of that is blood pooling, part of it is lymphatic fluid pooling. Right? So how do I get that blood then? Because if I start to exercise, we said Q has to go up. For Q to go up, EDV has to go up. So if I've got all this blood sitting in my veins, how do I get EDV to increase? I've got to find a way of moving that blood back towards the atria of the heart. Okay. First mechanism is venoconstriction. So when we look at veins in areas other than skeletal muscle, they have quite a high chat going on with the sympathetic nervous system. So when we start to exercise, those veins are constricted, and that helps push blood towards the heart. Right? It doesn't work in the skeletal muscle quite that way because the skeletal muscle doesn't have a lot of sympathetic stimulation in it. In the skeletal muscle, we have a mechanism called the muscle pump. So I've got lots of blood sitting in the gastrocnemius, in my quads, my hamstrings. How do I get that back? And what we see is that in the larger veins within the skeletal muscle, there's a valve that is a one-way valve. So when we start to move and the muscle is contracting, it squeezes the blood that's sitting in the large veins in the muscle up towards the heart. And because of the valve, as the muscle relaxes, so if I walk, right, my calf muscles are contracting and relaxing as soon as I start walking. So during the contraction, the blood that was sitting there gets squeezed up, and during the relaxation, during the swing phase, the valve, the blood tries to flow back, but the valve blocks the blood flow back. Right? So it encourages blood flow towards the heart. Sitting on a plane, one of the reasons they want you to get up and walk around, or at least to be moving your legs. Because what they found is that if you sit still for a very long time, particularly because they don't adapt the seats to fit 99% of the people that sit on the plane, so for a lot of us, the edge of the seat is pushing against the hamstring and stopping blood flow back to the heart through the hamstring. Right now they encourage you to move around or to move your feet, lift your knees up and down while you're sitting in your seat as much as possible to activate this muscle pump to try to push blood back towards the heart. Right? What they found on long distance flights, when I first started flying to the States, they would literally let you sit on the floor and do yoga for the whole flight. Then they went through a period of time where no one could get out of their seat, period. Didn't matter, it was a 10-hour flight. You could not leave your seat unless you were going to the toilet, and as soon as you came out of the toilet, you had to go back to your seat. Well, then what happened was a few people died, particularly on flights down to Australia, because that's a 24-hour flight. And when they investigated what was happening, other people passed out because, of course, if all the blood is pooling in my legs and my Q is low, then blood flow and oxygen to the brain is also low. So people would stand up and faint. A couple of people died because sitting there and letting the blood pool like that helped, facilitated blood clots. And then the blood clot would move around the body and cause a heart attack or a stroke. So they had quite a lot of problems. And now, at least on the flights that I use, they're much more, they don't quite let you sit down and do yoga anymore for the flight, but they're very encouraging of you getting up and walking up and down on a regular basis. And you're making sure that you move. They have little videos now that they play on a regular basis going, don't forget that you're supposed to be moving during the flight and things like that. So we've learned a lot physiologically about how this mechanism works. And then the last way that we get some additional blood moving back to the heart is via the respiratory pump, which is enhanced when we exercise because we breathe faster and we breathe more deeply. So when I breathe out, as we're about to cover, then pressure in the thorax goes up. When I breathe in, it goes down, and so there's this kind of wave of action in the respiratory muscles that's helping to push blood back towards the heart. So, particularly pay attention to our adaptations, right? Our adaptations are typically positive. If I'm exercising, then the whole point of exercising is to try and get something to happen that's going to make me better at what I'm trying to do. Otherwise, there wouldn't be any point in training. Okay. So, we've got adaptations in heart size. We see adaptations in heart rate, stroke volume, cardiac output, blood flow, blood pressure, and blood volume. And depending if you're a picture person, they have a nice set of graphs in the chapter that help to summarize. Here's heart rate against oxygen uptake, right? Stroke volume against intensity, Q against intensity, blood pressure to intensity, and VO2 to peak VO2. All right, so they've got some graphs if you like graphs. Some people don't find graphs useful, so use them as backup if visually and mathematically you like numbers, right? But you should be looking at, when you're studying, we know we see adaptations in all these factors when we do aerobic training. And some of those factors we also see adaptations to resistance training. Okay, so that brings us to how did we get the oxygen into the blood in the first place? Book kind of works backwards. The energy systems, and then we do muscle contraction, and then we do how do we get the blood to the muscles so the muscles can contract effectively, and now we do how do we get the oxygen into the bloodstream in the first place, because without the oxygen we can't work aerobically. Fingers crossed, this is not new, right? So AMP, I don't know how much work they do on the lungs and the respiratory system in AMP. Hopefully enough that this picture is not a novel idea for you. Right? What's our function of our respiratory system? Right? So it's moving air in and out of the lungs. That one's obvious. At the level of the alveoli, we see exchanges of gas between the air and the blood. So I have to get oxygen in, but I also have to get carbon dioxide out. Right? If you go back to your Krebs cycle, we make carbon dioxide. So carbon dioxide is a waste product. We have to get rid of it somehow. So it is absorbed into the bloodstream, and we exchange it at the lungs and get rid of it without any issues of toxicity or anything like that. So that's the major role of the system. I have to get oxygen into the bloodstream, I have to get carbon dioxide out of the bloodstream. And that doesn't occur when we look at the whole system. that doesn't occur until we're all the way at the bottom of the system. Right? So all these other structures that are involved in the respiratory system are not involved in that main function. They're involved in making sure that the air is damp, right? Because the membranes in the lungs and in the alveoli are very delicate, and if we did not have water vapor in the air and in the gases, then we would get some drying out. They would not be able to do their job properly. It also helps to warm the air. Right? So as I breathe it in, it warms as it goes down, makes transporting the oxygen out a little simpler at the end. And it filters the air for us. Right? Very important, particularly if we live in a polluted environment. Right? Our environment isn't horribly polluted. We do have a lot of allergens in our environment. Some of us are better at doing filtering on allergens than others. This morning on the playground was very hard work because it was so windy. There was a lot of dust and pollen and grass seeds and things blowing around. Right? So in theory, the mucus should trap anything that's in the air as you breathe it in, and then it gets breathed out when we breathe out. But it doesn't, anything that gets missed should get eaten by macrophages. Those that have really bad allergies know that the macrophages don't always do their job as well as they should. So we have to resort to puffers, we have to resort to allergy meds and things like that. So the humidifying, the warming, particularly in an environment where there's low humidity, right here. The higher the altitude, the less water vapor there is in the air. So we're at about 4,000 feet. Doesn't feel high because we've been here for a while, and when you walk out, it's flat as a pancake as far as you can see. So it feels like we're at sea level, but we're nowhere near sea level. So physiologically, this is quite challenging here. Right? It also is colder. Okay? Air temperature is colder the higher you go. So generally, the temperatures in Albuquerque are cooler than they are here, because it's another 2,000 feet or so into Albuquerque. So at the end of the system then, once I've breathed in and we go into the lung tissue is made up of tiny little sacs called the alveoli, which are surrounded by capillaries, and that's a key point. Remember that at the alveoli, that's where our gas exchange is occurring, so we want as much blood flow around the alveoli as possible. And somewhere around 300 million alveoli in a typical set of lungs. So that's kind of an abstract number. It's pretty impossible, I think, to really visualize what 300 million alveoli are like. But if you take those 300 million alveoli and you lay them out, so instead of all being little round sacs, we take all that surface area from those little balls and we lay it out flat, that would cover a tennis court. So the surface area is the key here, right? The direct link to the bloodstream and the amount of surface area that is provided because we've got little sacs instead of flat tissue. Okay? It's a bit like when you look at the brain, right? the brain's all wibbly wobbly and curvy and bumpy. The whole point of that is to provide extra surface area for oxygen and nutrition. So, same thing occurs with our lungs. It's just a really clever adaptation as we developed that we don't have a flat surface in our lungs.
So does smoking change the surface area?
So one of the things that happens with smoking is, depending on what you smoke, but if you're smoking cigarettes and things, they have tar. And the tar gets down and kind of decreases the area for the air to pass through. So it's a bit like plaque in the bloodstream, decreases the diameter of the blood vessel. Tar decreases the diameter of the bronchioles, and then once you get to the, I think it mainly impacts the bronchioles, but then the amount of oxygen you can get into the bloodstream gets impacted because carbon monoxide sits on the hemoglobin where the oxygen is supposed to go. So your oxygen stats go down, and so this exchange is not very efficient because you don't have as much oxygen available as you should have. So the respiratory membrane, when we're looking at this exchange, okay, I've got to get the blood as close to the lung as I possibly can. All right, so here's my bloodstream, and here is my lung, alveoli. So the respiratory membrane is the combination of these two membranes within these systems. So, here's my red blood cell. Here's the outside wall of the capillary. Here's the gap. Here's the inside wall of the alveoli. And that's where the gas is coming from. So if you dissect through the alveoli, here, this diagram is, I think, really a cool visual, because that one gives you that idea of the sac being completely surrounded by blood vessels. Okay, so I'm going to breathe in. I'm going to have air in my lungs. I've got to get the oxygen out of my lungs and onto the bus, onto the red blood cell. So last week we said that we have to follow the laws of physics when we look at blood flow, or water flow, or gas, movement of gases and molecules. So it goes from where to where. When we look at the movement of fluids or gas or molecules, go from an area of what? Goes from an area of high pressure or content to an area of low. Always, always. That's just the rule. Right? Everything goes from high to low. So, in order to get air into my lungs then, the pressure of the air outside has to be higher than the pressure inside. So if my intrathoracic pressure is lower than the atmosphere, air can move in. If I want to get air out, if I want to breathe out, now the pressure inside my chest has to be higher than the pressure outside so the gas can move out. So I have to be able to create the change of pressure within my chest cavity. So to inspire, right, breathe in, I increase the lung volume, I decrease the pressure, and that causes air to rush into my lungs. So when we breathe in, we don't exactly breathe in, we just change the pressure by moving our rib cage, and that causes air to move into the lungs. When we breathe out, we decrease the lung volume, and that increases the pressure, and that moves the air back out again. The lung tissue itself doesn't have any contractile element. It can't contract. Lungs do not contract and expand, right? It's just a flobby mass of cells. If you go, you guys don't really have butchers, but if you have the opportunity, or if you live near a farm, or go and see what a lung looks like. It's just, right? It doesn't do anything on its own. It's like a skeleton, right? It's great and it's useful, but it can't move. It has no contractile tissue within it. So for the lungs to expand and contract relies completely on other mechanisms to change the volume. So when I breathe in, your diaphragm, which is a big sheet of muscle, flattens as it contracts, right? And it runs right across the top of your stomach there, right? So when I breathe in, the diaphragm is contracting and relaxing. But to breathe out, really I don't have to necessarily, right? I don't have to contract muscles, I just have to stop breathing in. And as they relax, the air moves out. So we don't typically have to work very hard to breathe out when we're exercising. Most of the work is breathing in.
So does this change whenever someone's like on oxygen? With that constant pressure flowing into their face?
If they've got an oxygen mask on, then what that does is it increases the concentration of oxygen here and allows more oxygen to get across into the bloodstream because it goes high to low. So by using an oxygen mask, it enables more oxygen to get across into the bloodstream. So it doesn't change the breathing in and out that I've heard of. I suspect they have the pressure of the oxygen in the tank relatively neutral to the air. Otherwise you have to work harder and that would be defeating the object. So how easy is it to move the air in and out of the lungs? Okay? The resistance to airflow works exactly the same way as the resistance to blood flow that we talked about last week. Right? I have a pressure difference, because it's got to go from high to low, and the resistance between two areas. So I can amplify the pressure difference if I want to increase airflow, or I can decrease resistance to airflow. So this is your smoking cue. The diameter of the airway is the biggest factor to resistance to airflow. So if I decrease the diameter of the airway, then I decrease the ability to move air in and out of the lungs. A very interesting idea when you look at ballet dancers or sports where smoking is kind of part of the norm, part of the culture, because physiologically it doesn't make any sense. Dancers are terrible, terrible, terrible. They're one of the worst populations for smoking because dancers tend to use smoking as an appetite suppressor because they've all got to be, right? So they don't want to eat anything and so they smoke like crazy. But it doesn't make any sense physiologically to smoke that much and then try to dance for 4 hours. So it's a really interesting situation when you look at sports and activities where smoking is kind of part of the culture. When we exercise them, we stimulate bronchodilation in the lung tissue. So the bronchioles expand to allow more airflow into the lungs. If I have asthma, that doesn't work because the bronchioles are stiff and tight, and you may have mucus, which is similar to like a less toxic version of smoking. Right? So if I have asthma, I can't bronchodilate very well, and so then when I exercise, it becomes harder and harder because I'm not able to get enough oxygen into the bloodstream because I can't get enough air into the lung tissue. And so we use puffers and other forms of meds to help us bronchodilate as best we can. But someone with asthma doesn't even with help, is not going to have that mechanism working as efficiently as it should be. So you've got to pay attention if you've got people in your PE class or athletes on your team who are asthmatic, then you need to pay attention to, do they have their meds? Right? If they're struggling, can I decrease the intensity of the workout or the duration of the workout for them? When we start to exercise, and again, you might not have noticed, so next time you go out and you do an aerobic session, pay attention to what happens. At some point, your brain will switch you over from breathing through your nose to breathing through your mouth. Because that passage from your mouth to your lungs is bigger than the passage from your nose to your lungs. So if you're out for a nice run, or you're out on your bike, and you're trying to breathe through your nose because you have allergies, and my mouth isn't full of cilia to filter out the allergens, my nose is, so we try to breathe through our nose, because that's the best way to filter allergens. And after a few minutes, or depending on how fast you're going, without realizing it, you'll catch yourself breathing through your mouth. Because your brain says, well, I can't, the diameter of the airway from the nose is too small. I need more oxygen. I'm going to breathe through my mouth. Which is why sometimes using a mask, if you want to run and you have bad allergies, could be helpful. It's why the recommendation is if allergens are really high in the environment on a particular day, perhaps move your training plan indoors for the day. Because it's really hard. Once your brain has decided it wants to breathe through your mouth, it's actually pretty difficult to go back and start breathing through your nose. Give it a try next time. You can do it, but then you feel like you're catching for air all the time. Okay? So it's really quite, we don't even realize, our brain just subconsciously switches us over to make airflow as efficient as possible. The other thing that's in the news quite a lot when we look at airflow resistance is those little nasal strip idea. You see quite a lot of athletes using those. The research says there's no physiological benefit to airflow. However, there is some research that suggests there might be a placebo effect. So there's the belief that it's going to help me, and so it seems to help. But there's no physiological research that says sticking a strip on makes any difference to oxygen saturation and aerobic work. Okay? All right, pulmonary ventilation is the fancy term for breathing. I don't know why we have to have a fancy term, but it just means breathing. So how much air moves in and out of the lungs at any given time. So this piece of information is again very similar to the idea that we have with the heart, how much blood moves in and out of the heart within a given period of time. Okay. So tidal volume then is the amount of air moved per breath. It's the same idea as stroke volume, the amount of blood moved per beat. So tidal volume is the respiratory equivalent of stroke volume. The volume of air moved per minute would be the same as Q, the volume of blood moved per minute. And volume of expired air is tidal volume times frequency. So frequency, how many times do I breathe? Just like heart rate, how many times does my heart beat? Tidal volume, how much air am I moving every time I breathe, gives me the expired amount of air across a minute. That's typically much higher in athletes, not because our lungs grow, but because our respiratory muscles get stronger, and so the amount of change in pressure they're able to create increases. So what happens to frequency and depth of breathing? When you're sitting at rest, you're really not aware of your breathing very much, unless you're struggling, if you're not feeling very well, or you've got a cold, right? Unless there's a problem, when we're sitting at rest, we really don't pay very much attention to breathing. So you breathe quite shallowly. You're not sitting in your chair taking a great big deep breath. So your breathing is quite shallow when you're at rest, and it's also pretty slow. Right? I'm not sitting there going so it's shallow and it's slow, and I'm not consciously thinking about it, so it's being maintained by respiratory centers in the central nervous system and in the brain. Okay? When I start to exercise and we stress the system, everything changes. Right? The first thing that happens is that you start to breathe more deeply. So when you start to exercise, you don't start breathing very quickly. First thing that changes is instead of breathing shallow, you start to if you keep pushing the system, if you keep stressing the system, if you up the intensity or you up the duration, if the depth doesn't suffice, if that doesn't provide enough oxygen to the bloodstream, then you'll start breathing faster as well. So you guys will work out quite hard. Typically, when you're working out, you're going to see that you're breathing more deeply, but you're also breathing quicker than you do when you're at rest. So I can move at rest somewhere around 8 liters a minute. Right, that's typical. When you're exercising, if you're an endurance athlete, they can move 183 liters per minute. Massive amount of gas moving in and out of the lungs. So some of that is genetics. Right? The frustrating thing with exercise physiology often is that we come in and we've been told for so long that we can do anything we want to do if we just try hard enough and we work hard enough. That's not true. Right? It's not true when we look at muscle fiber type. I can't be quick if I'm born slow. It's not true when we look at strength development, and it's not true when we look at airflow. Right? Some people are genetically gifted with better airflow. Right? Some of it is a little bit of training. So I can make the respiratory muscles stronger. I can pay more attention to my breathing and try to alter what I'm doing. Okay, so I breathe in, I inspire, I change the volume so that it is lower than the outside atmosphere and air rushes into my lungs. Now the air is in the lungs, I have to get the oxygen out and into the bloodstream. So I've got this very large surface area. That's one factor that helps a lot. This respiratory membrane is very, very narrow. Right? I've got one cell in the wall of the alveoli and one cell in the wall of the capillary at this point. And so there's very little distance between the inside of the lung and the inside of the blood vessel. Right, so the distance that the oxygen and the carbon dioxide have to move from one place to the other is not very large. And we have pressure differences that help us out a lot, because we can go from high to low. So partial pressure is the term used for the percentage pressure for a particular gas. Right, so we're most interested at the moment in oxygen. We're going to look at the partial pressure of oxygen. All right, so lung, breathe in. Doesn't like it when I go to put the lid on. Okay? I want the oxygen into the bloodstream. Yes? So in that particular instance, where is high and where is low? Alright, so for this, So when we look at the partial pressure of oxygen, it's higher in the lung than it is in the bloodstream, and that facilitates oxygen moving across the membrane into the bloodstream and jumping onto a hemoglobin bus if we're not anemic. Assuming that we've got lots of red blood cells with lots of hemoglobin, I want as much oxygen as possible getting across that membrane so that I can fill up the hemoglobin and saturate my bloodstream with oxygen. If I want to get rid of carbon dioxide, where's high and where's low? So when you're looking at this information, don't make the mistake that one side of the membrane is high and one side of the membrane is low. Because that's not the case. It depends what you're investigating. Right? The molecule moves from high to low. So if you imagine that your molecule is a little hot. Right? So if I park my car at the top of a hill, and the hill is very, very steep, and I take the handbrake off, what happens to the car? Goes down the hill, right? Fast or slow? Picks up speed. It's quite fast. Okay? So the steepness of the gradient from high to low impacts how quickly and how much oxygen or carbon dioxide can move across. If I park my car on a hill that isn't as steep and I take the handbrake off, what happens?
It'll slowly roll.
It'll slowly roll down the hill, right? So if my pressure gradient is less steep, I can still get oxygen across the membrane, but it doesn't move as quickly as when the gradient is very steep. What about if I park my car on the flat and I take my handbrake off? There's no movement, right? So if there's no pressure gradient, if the pressure, partial pressure for that molecule is the same on both sides of the membrane, nothing goes anywhere. Right? With me so far? Okay, so on Wednesday then we're going to look at what that means when we look at the system.